In the previous video, we showed how the square of an odd integer has the form of 8m plus 1 for some random integer m. And the trick in that problem was to divide the integer n by 4 and look at the possible cases of the remainders. And again, when you divide the integer n by 4, there are 4 things that could happen. You're going to end up with 4k plus 0, or 4k plus 1, or 4k plus 2, or finally 4k plus 3. And we said that out of those cases, 2 of them were impossible because the integer was odd. That left us with 2 cases to try out and verify that when you square them, they both give the correct solution, the correct form that we wanted. Now, why did we divide by 4? How did we know to divide by 4? This comes with a little bit of experience and just doing some homework assignments. Dividing by 2 did not obviously work. We tried that on scratch paper first, so then we decided to divide by 4 and look at the remainders. And the remainders were 0, 1, 2, 3, and some of them were not legit. So we could eliminate those cases and we're left with 2 cases. So we verified that they both work. So this was a true statement and we proved it in another video. Let's take a look at another problem now. In this case, we want to show that every prime number, except for the primes 2 and 3, every prime number out there has the form of 6q plus 1 or 6q plus 5 for some integer q. So again, take a prime number, for example, 7, and 7 is promised to be either 6q plus 1 or 6q plus 5. In this case, actually, 6q plus 1, where q is equal to 1. I could try it again with another prime number, for example, 29. What would 29 look like? Is it form 1 or form 2? Well, 6 times 4 plus 5 is going to be 29. So 29 looks like the second form, whereas 7 looks like the first form. Now, this is a true statement, and how do you go about solving and proving it? Pause the video and see if you can do this yourself before watching the rest of the video. So we're going to begin by taking a prime number and dividing it by 6. Why am I dividing it by 6? Well, in my question, they want me to show that the prime number looks like 6q plus 1 or 6q plus 5. So I'm seeing 6 in front of both of those forms. So it makes sense to divide the prime number by 6. And keep in mind that the prime number is not allowed to be 2 and 3. So I'm going to choose a prime number, and I'm going to suppose that the prime number is not the number 2 or the number 3. And dividing it by 6, and the quotient remainder theorem gives me that the prime divided by 6 is going to have 6 possible remainders, either 0 or 1 or 2, all the way to 5. And so we're going to systematically eliminate some of these remainders that lead us to some false conclusions, so to some crazy nonsense, basically. For instance, all the remainders 0, 2, 3, and 4 lead to some crazy results. Let me show you. If the remainder is 0, then my prime number looks like 6q plus 0. But this means that the prime number can be written as 2 times 3q. Remember, the 6 is 2 times 3, so that's what I'm doing here. I'm breaking it down into 2 times 3, which now means that the prime number is an even integer. But remember, the only prime number that is even is the number 2, and we had said the prime that we're choosing is not 2. So this case cannot happen. So the remainder 0 is automatically eliminated. And we could do the same thing again with the remainder 2. If the remainder was 2, then my prime number looks like 6q plus 2, which can be factored into 2 times 3q plus 1. Now keep in mind that q is an integer, so this implies that 2 is dividing p. Another way of saying that is to say that p is now an even integer. But remember, the only prime number that is even is 2, and our prime is not the number 2. We had made that choice on purpose. So that's automatically another case that we can completely eliminate. So remember, the possible remainders were 0, 1, 2, 3, 4, and 5, and we're pretty much going through and eliminating some choices that don't make sense. So far we have eliminated 0 and 2. And we're going to look at the possible remaining remainders. Again, turns out that 3 and 4 could not possibly be true. So 3 is going to be eliminated next, and 4 is going to be eliminated afterwards, leaving us with 2 possible remainders, which are the remainders that we're looking for, basically. So let's continue. If the remainder is 3, then my prime number would have the look of 6q plus 3. This means I can factor a 3 now, and that means 3 is now a factor of the prime number p. So 3 divides p. This can only happen if the prime itself is 3, but remember, we said that the prime is not supposed to be chosen as 3. So this case cannot be true either. Now what about when the remainder is 4? If the remainder is 4, then my prime number looks like 6q plus 4, which means again I can factor a 2 out of this. 6q plus 4, we can factor a 2 out, and that leads to the conclusion that 2 is a factor of p. In other terms, this leads to saying that p is an even integer that is prime, and the only prime number that is even is 2, but we said that this case cannot happen. So we're left with the only other 2 remainders, 1 and 5, and in both cases, the prime number has the desired look. If the remainder is 1, then our prime number looks like 6q plus 1. If the remainder is 5, then the prime number has the look of 6q plus 5, in which case we are happy. So in conclusion, every prime number except for 2 and 3 has the form of 6q plus 1 or 6q plus 5. And we did this by pretty much process of elimination. We kind of took out all the impossible remainders and we're left with 2 remainders. So my prime number is either going to have one of those 2 remainders. Don't know which one, but it's one of those 2.